The universe is only 13.8 billion years old, yet the region we can observe spans nearly 93 billion light-years across, more than 3 times what that age should permit. This is a scale that should not exist under simple cause and effect reasoning. Light has a finite speed and a finite amount of time to travel. Yet the most distant galaxies we see are far beyond the maximum distance light should have been able to reach. According to basic intuition, nothing should appear farther away than the age of the universe allows. Yet, modern measurements show the observable universe is more than 3 times larger than that limit. If cosmic expansion followed common sense, the observable universe would end at 13.8 billion light-years. But precise observations place its boundary tens of billions of light-years farther out. We measure the universe's age with high precision, yet the size of the observable universe is so much larger than that age permits that it forces a redefinition of what distance actually means. For decades, the simplest explanation felt sufficient. The universe has a known age. Light moves at a known speed. Put the two together, and the maximum scale of what we should be able to observe seems obvious, clean, intuitive, settled. But observations refuse to cooperate. When astronomers map the cosmos using modern instruments, they find that the observable universe has a radius of about 46.5 billion light-years and a diameter approaching 93 billion light-years. These numbers are not speculative. They are not controversial. They are the direct outcome of how distance behaves in an expanding universe. And this is where the tension peaks. Because once distance stops behaving the way we expect, every timeline built on that expectation comes under pressure. How quickly galaxies formed, how early massive black holes appeared, and how representative our past surveys really were. The James Webb Space Telescope pushed this tension into the open. Its deep field observations revealed crowded regions where emptiness was assumed, and early structure where simplicity was expected. Not because the universe suddenly changed, but because our ability to measure it did. If this moment makes you pause, if it challenges how you've always pictured the universe, take a second to like and subscribe this video. It helps more people encounter these questions. And if you want to follow where this evidence leads next, subscribing keeps you part of that journey. Because what follows is not a list of discoveries. It is an examination of how those discoveries force science to adapt. In this video, you will see what distance actually means when space itself expands, and why the simple math fails. You will see how Webb's infrared vision reshapes the census of galaxies, and how that reshapes estimates of stars, planets, and structure. You will see why claims of too much light too early are not conclusions, but stress tests. And you will learn where modern cosmology draws the line between direct measurement and calibrated inference. These measurements are not trivia. They shape the history of cosmic structure. They constrain the physics of dark matter and dark energy. and they test whether the standard cosmological model remains a reliable predictive framework as our instruments improve. This is not a story about spectacle. It is a story about how scientific knowledge changes, quietly, methodically, when observation outruns assumption, when astronomers say they are looking back in time. They are not using a poetic phrase. They are describing a physical limitation. Light does not arrive instantly. Every photon you detect has already traveled for some amount of time before it reaches an instrument. The farther away the source is, the longer that journey takes. So when you observe a distant object, you are not seeing it as it exists now. You are seeing it as it was when the light left it. That is the starting point of all astronomy. And it immediately creates confusion because several ideas that sound similar are not the same thing at all. Distance is not look-back time. Look-back time is how long the light has been traveling. Distance is where the object is located now, not where it was when the light began its journey. In an expanding universe, those two numbers can differ dramatically. The age of the universe is not the age of an object. The universe may be 13.8 billion years old, but an object observed at high look-back time could have formed hundreds of millions of years after the Big Bang. When astronomers say they are seeing a galaxy from the early universe, they are referring to the epoch in which the light was emitted, not the total age of everything that exists. Observed brightness is not intrinsic brightness. A distant object can appear faint for several reasons. It may actually emit very little light, or it may emit a great deal of light that is spread out over an enormous distance, or its light may have been shifted into wavelengths that an instrument cannot detect efficiently. Without correcting for these effects, brightness alone tells you very little. These distinctions matter because astronomy does not work by direct inspection. It works by reconstruction. Astronomers never observe an object itself. They observe photons that arrive at a detector. Those photons pass through an instrument with known sensitivities and limitations. The raw signal is then calibrated to remove noise, background effects, and instrumental bias. Only after that process do scientists begin comparing the data to physical models. Every result you hear about follows that chain. Photons reach a detector. The detector records a signal. That signal is calibrated. The calibrated data is compared to models. The models produce interpretations. At no point is there a shortcut. This is why astronomy is cautious by design. Any single measurement can be misleading. Any single indicator can point in the wrong direction if taken out of context. And this is where redshift becomes central. Redshift is not a secondary detail. It is the backbone of modern cosmology. Operationally, redshift is measured through spectroscopy. Atoms emit and absorb light at very specific wavelengths. Hydrogen, for example, produces a distinct pattern of spectral lines. When astronomers observe those same lines shifted toward longer wavelengths, they know the light has been stretched during its journey. That stretching is quantified. The amount of shift can be measured precisely, but redshift alone is not distance. Redshift becomes distance only when it is interpreted through a cosmological model that describes how space itself expands over time. That model links the amount of wavelength stretching to the expansion history of the universe. This is why redshift measurements are powerful, but never stand alone. Astronomers do not trust single indicators because the universe offers too many ways to be misleading. Dust can dim light. Gas can absorb specific wavelengths. Bright objects can masquerade as massive ones. Black holes can inflate luminosity estimates. So confirmation requires convergence. Independent measurements using different methods must agree. Spectroscopy must align with photometry. Distance estimates must be consistent across multiple indicators. Models must reproduce not just one observation, but entire populations. When those independent lines of evidence converge, confidence grows. When they do not, the model is questioned, not the data. And that discipline is what allows astronomy to move forward, even when new instruments like Webb expose limits that were previously invisible. Before Webb, modern cosmology was built largely on the view provided by the Hubble Space Telescope. That view was not narrow, it was transformative. Hubble operated for decades, delivering consistent, high-resolution imaging across a wide range of targets. Its longevity mattered. Observations taken years apart could be compared directly. Calibration improved over time. Patterns emerged not from single images, but from accumulated evidence. One of Hubble's most influential contributions was its deep field work. By staring at small regions of sky for extended periods, Hubble revealed thousands of galaxies where only darkness had been expected. These observations demonstrated that the universe is densely populated, even in regions that appear empty to the naked eye. Over time, repeated deep field campaigns produced a coherent picture. Galaxy counts rose predictably with depth. The distribution of brightness and size followed patterns that could be modeled. Redshift measurements place these galaxies across a broad span of cosmic history. Hubble also played a central role in refining distance measurements. By observing standard candles and calibrating multiple distance indicators, it helped establish the expansion rate of the universe and confirmed that expansion is accelerating. These results anchored the standard cosmological model and provided a framework for interpreting galaxy formation over time. Taken together, Hubble's observations produced what scientists considered a baseline expectation. How many galaxies should exist in a given volume? How early large structures should appear? How brightness should decline with distance and time? These expectations were not arbitrary. They were grounded in decades of consistent data, collected with a well-understood instrument. But consistency does not guarantee completeness. Hubble's strengths were tied directly to its design. It was optimized primarily for visible and ultraviolet light, with limited infrared capability. That optimization made it extraordinarily effective at studying nearby galaxies, star-forming regions, and objects whose light had not been heavily redshifted. It also created a boundary. Light from very distant galaxies is stretched by cosmic expansion. As redshift increases, emission that began in the visible range moves into the infrared. Beyond a certain point, those signals fall outside the range where Hubble could detect them efficiently. Dust adds a second limitation. Star formation often occurs inside dense clouds of gas and dust. Dust absorbs and scatters visible light, dimming or completely obscuring regions that may be extremely active. Infrared light passes through dust more easily, but Hubble's infrared sensitivity was limited. These are not failures. They are design trade-offs, but they introduce a crucial effect. If an instrument is insensitive to certain wavelengths, it will systematically undercount objects whose signals lie in those wavelengths. The resulting survey can be accurate for what it detects, while still missing entire populations. This is what astronomers mean by selection effects. A survey does not sample the universe evenly. It samples the universe through the filter of the instrument used. Objects that fall outside that filter are not absent. They are simply unobserved. This creates a subtle form of observational bias. Not bias in the sense of error or misconduct, but bias in the sense of limited visibility. The conclusions drawn from the data reflect what the instrument could see, not everything that existed. Hubble's surveys were internally consistent. They agreed with each other. They aligned with models built to interpret visible light data. That consistency reinforced confidence, but it also meant that entire classes of faint, red-shifted, or dust-obscured objects contributed little to the picture, not because they were rare, but because they were difficult to detect. As long as no instrument could access those signals effectively, the baseline remained stable. Webb changed that by extending sensitivity deeper into the infrared and pushing detection limits far beyond previous surveys. Webb began revealing populations that had been largely invisible before. And once those populations appear, the question is no longer whether Hubble was right. The question is how much of what we thought we knew was shaped by what Hubble could not see. The James Webb Space Telescope looks the way it does because it was built to answer very specific questions. Every major design choice reflects an assumption about where previous observations were failing and what kinds of signals were being missed. Start with the mirror. Webb's primary mirror is more than 6 meters across. That size is not about prestige. It is about sensitivity. A larger mirror collects more photons, and when you are trying to detect objects that are extremely faint, collecting more photons is the difference between seeing something and seeing nothing at all. But mirror size alone is not enough. Webb was designed primarily as an infrared observatory. That decision shapes everything else. Light from very distant objects does not arrive at Earth in its original form. As the universe expands, wavelengths stretch. Radiation that began as ultraviolet or visible light arrives as infrared. The farther back in time you look, the more extreme that stretching becomes. Previous telescopes could access some infrared wavelengths, but not with the sensitivity needed to study the earliest galaxies in detail. Webb was built to operate across a wide infrared range, specifically to capture light that had been shifted beyond the reach of older instruments. That choice immediately implied a second requirement. Infrared detectors must be kept extremely cold. Any warm object emits infrared radiation. If the telescope itself is warm, its own heat overwhelms the faint cosmic signals it is trying to detect. So Webb operates at very low temperatures, far from Earth's heat, with a large sun shield blocking radiation from the Sun, Earth, and Moon. This requirement leads directly to Webb's orbit. Webb does not orbit Earth. It operates near the second Lagrange point, known as L2, about 1 million miles away. At this location, the gravitational pull of the Sun and Earth allows the telescope to maintain a stable position relative to both. That stability matters. At L2, Webb can keep its sun shield oriented in one direction continuously. The thermal environment remains predictable. The instruments stay cold. The background noise stays low, and long, uninterrupted observations become possible. All of this reflects an underlying idea. Instrument design is a theory about what matters. By building a large, cold, infrared-sensitive telescope and placing it in a stable, distant orbit, scientists were betting that the most important missing information lay in faint, red-shifted signals from the early universe and from dust-obscured regions that visible light could not penetrate. Webb's design assumed that galaxies formed earlier than we could previously see, that star formation often occurred inside dusty environments, and that critical phases of cosmic history were effectively hidden from older surveys. The telescope was not built to confirm what we already knew. It was built to test where our view had been incomplete. That design philosophy becomes most visible in Webb's deep field observations. A deep field is not just a beautiful image. It is a deliberate statistical experiment. The idea is simple. Point the telescope at a small patch of sky that appears empty. Then, observe it continuously for a very long time. Combine thousands of exposures. Push the detection limit as far as possible. The result is a census of everything in that direction, down to the faintest measurable level. The immediate objection is obvious. How can a tiny patch of sky represent the universe as a whole? The answer depends on what you are trying to measure. If the universe is homogeneous on large scales, then small, randomly chosen regions should, on average, reflect the broader population. Deep fields allow astronomers to probe very faint objects, that would be impossible to detect across the entire sky. This is where small samples become powerful. They let you explore the extremes, the faintest galaxies, the earliest epochs, the low signal populations that dominate number counts but not brightness. But small samples also carry risk. The universe is not perfectly uniform on smaller scales. Some regions are denser than others. Some contain more galaxies, some contain fewer. This variation is known as cosmic variance. If you observe only one small region, you might accidentally choose an area that is unusually crowded or unusually empty. That can distort conclusions if it is treated as typical. This is why multiple deep fields matter. By observing small patches of sky in different directions, astronomers can compare results. If independent deep fields show similar galaxy counts, similar brightness distributions, and similar redshift ranges, confidence increases that the findings are not artifacts of location. If they differ significantly, that difference becomes data. Deep fields are not meant to replace wide surveys. They complement them. Wide surveys map large-scale structure at lower sensitivity. Deep fields map the faint end of the population at extreme depth. Together, they allow astronomers to test whether earlier conclusions were limited by visibility rather than by physics. And that is exactly where Webb has had its strongest impact. By combining its engineering choices with deep field strategy, Webb did not simply extend existing observations. It exposed the boundaries of what older instruments could never see. And once those boundaries are crossed, the question is no longer whether the universe changed. The question is, how much of our previous understanding was shaped by what remained invisible at the time? The first mistake most people make when thinking about the size of the universe is also the most natural one. The universe is 13.8 billion years old. Light travels at a fixed speed, and so it seems reasonable to conclude that the farthest anything could possibly be is 13.8 billion light-years away. That logic feels complete because it mirrors how distance and time work in everyday experience. But it quietly assumes that the space between a distant object and an observer remains fixed while light is in transit. And in an expanding universe, that assumption does not hold. When a distant galaxy emits light, that galaxy does not remain at the same separation while the photon moves toward us. Throughout the entire journey, the space between the galaxy and Earth continues to expand, meaning the photon is traveling through a distance that is itself changing. As a result, what the light has traveled and where the source is now are not the same thing. This is why astronomers are careful to distinguish between different meanings of distance. One meaning is light travel distance, which is tied directly to lookback time and tells us how long ago the light was emitted. Another is comoving distance, which describes where the object is located now after accounting for the expansion that occurred while the light was traveling. In a universe that did not expand, these values would be identical. But in our universe, they diverge dramatically. A galaxy whose light has been traveling for nearly the entire age of the universe was significantly closer at the moment of emission, and the expansion that occurred afterward increased its separation continuously. By the time that light arrives at our detectors, the galaxy's current distance can be tens of billions of light years greater than the distance the photon actually crossed. This difference is the reason we can observe objects that are now more than 40 billion light years away without violating any physical limits. The photon did not exceed the speed of light, and nothing outran causality. Instead, the space the photon was moving through expanded, while the photon was in transit. This same logic explains why astronomers sometimes say that very distant galaxies are receding faster than light, a statement that often sounds alarming, but is frequently misunderstood. No object locally moves through space faster than light, and the constraints of relativity remain intact. What exceeds the speed of light is the rate at which separation grows between distant regions due to the expansion of space-time itself. This is not motion through space in the everyday sense, but a property of the universe's large-scale geometry. Once this is understood, the large size of the observable universe stops appearing paradoxical. When astronomers calculate the observable radius of roughly 46.5 billion light years and a diameter near 93 billion light years, they are not measuring how far light has traveled. They are measuring how far away the sources of that light are today, given the universe's expansion history. A simple illustrative example helps clarify this. Imagine a galaxy observed at extremely high redshift. When that galaxy emitted the light we detect now, its distance from us might have been only a few billion light years. Over the next 13.8 billion years, expansion steadily increased the separation. By the time the light arrives, the galaxy's present-day comoving distance could be many times larger than the distance that photon originally crossed. This example is not a claim about a specific measured object, but a way to build intuition about how expansion reshapes distance over time. With this reframing, the size of the observable universe is no longer a contradiction, but a consequence of how space evolves. The numbers are large because expansion has been acting for nearly the entire history of the universe, stretching separations far beyond what simple intuition predicts. This shift in understanding does more than resolve a single calculation. It changes how horizons are defined, how observational limits are interpreted, and how much of the universe is permanently inaccessible to us. And once distance itself is understood as something dynamic rather than fixed, it becomes clear that every other measurement we make at cosmic scales depends on this same framework. When Webb began returning its deepest images, the most immediate change was numerical. In regions of sky that had already been studied extensively, galaxy counts increased by orders of magnitude. Areas where Hubble surveys had identified on the order of 10,000 galaxies now yielded catalogs approaching 800,000 distinct objects when analyzed with Webb's infrared data and modern processing techniques. This was not a matter of Webb simply looking longer at the same scene. It was the result of accessing wavelengths that had been largely unavailable before, combined with improvements in how faint signals are extracted from background noise, light that had been stretched far beyond the visible range by cosmic expansion, and light emerging from regions heavily obscured by dust suddenly became detectable. Objects that previously appeared as faint, unresolved patches were separated into individual sources. Once infrared sensitivity and resolution were combined with large-scale data stacking. Dust plays a central role in this change. Star formation often occurs inside dense, dust-rich environments that absorb visible light but allow infrared radiation to pass through. In visible light surveys, these regions can appear dim or absent, even when star formation rates are high. Webb's infrared instruments are sensitive to this emission, allowing entire populations of galaxies to emerge where earlier surveys recorded little or nothing. At the same time, advances in image processing matter. Webb's deep fields are built from thousands of individual exposures combined through carefully calibrated pipelines. This stacking increases sensitivity and allows astronomers to distinguish real sources from noise with far greater confidence than was possible in earlier eras. The result is not just more light, but more reliable detection of extremely faint objects. A catalog containing hundreds of thousands of objects, however, does not mean that each entry is equally well understood. Detection and classification are not the same thing. Detection establishes that a source exists above a defined confidence threshold. Classification attempts to determine what kind of object that source is. Photometry measures brightness across different wavelengths, providing color information and rough physical properties. Morphology describes shape and structure, which becomes more uncertain as objects grow fainter and smaller in apparent size. Redshift estimation can be inferred statistically from photometric data, but spectroscopic confirmation requires much more observing time and is available for only a fraction of sources. Large catalogs, therefore, contain layers of certainty, with some objects characterized in detail and others represented primarily as statistically significant detections. This shift in scale changes how astronomy operates. Instead of focusing primarily on a small number of exceptionally detailed objects, research increasingly relies on population statistics. Distributions, trends, and correlations across tens or hundreds of thousands of galaxies become more informative than any single example. Questions move away from whether a particular galaxy is unusual and toward how common certain properties are across cosmic time. This does not eliminate the value of detailed follow-up observations, but it does change where confidence comes from. Patterns seen consistently across large samples carry a different weight than isolated discoveries. The increase in galaxy counts also has broader implications. If the total number of galaxies in the observable universe is higher than previously estimated, then the inferred number of stars and planets scales accordingly. If each galaxy hosts billions of stars, And if many of those stars host planetary systems, then increasing the galaxy count by an order of magnitude increases those totals by the same factor. This scaling is mathematically straightforward, but it rests on assumptions that require careful testing. Deep fields sample small regions of sky, and those regions may not be perfectly representative of the universe as a whole. Cosmic variance means just that some areas are denser than others. For this reason, astronomers are cautious. Wider area surveys at slightly lower depth are underway to determine whether the high densities seen in deep fields persist across different directions and environments. An illustrative scenario helps clarify how this scaling works. Imagine that a previous estimate placed the total number of galaxies at 200 billion based on visible light surveys. If new infrared observations suggest that the true number might be 10 times higher, then estimates of total stellar populations and potential planetary systems also increase by roughly the same factor. The scaling itself is valid. What remains under refinement is the initial input value. As more surveys expand coverage and improve completeness, that number will be adjusted, constrained, and potentially revised again. What Webb's deep fields have done is not to provide a final count, but to demonstrate that earlier counts were incomplete in a systematic way. By revealing large populations of faint, red-shifted, and dust-obscured galaxies, Webb has shifted the baseline expectation. The universe appears more crowded than it did before, not because galaxies suddenly formed, but because instruments finally became capable of detecting them. And once that baseline shifts, every inference built on it must be revisited with the same level of care. When Webb began returning its deepest images, the most immediate change was numerical. In regions of sky that had already been studied extensively, galaxy counts increased by orders of magnitude. Areas where Hubble surveys had identified on the order of 10,000 galaxies now yielded catalogs approaching 800,000 distinct objects when analyzed with Webb's infrared data and modern processing techniques. This was not a matter of Webb simply looking longer at the same scene. It was the result of accessing wavelengths that had been largely unavailable before, combined with improvements in how faint signals are extracted from background noise, light that had been stretched far beyond the visible range by cosmic expansion, and light emerging from regions heavily obscured by dust suddenly became detectable. Objects that previously appeared as faint, unresolved patches were separated into individual sources once infrared sensitivity and resolution were combined with large-scale data stacking. Dust plays a central role in this change. Star formation often occurs inside dense, dust-rich environments that absorb visible light, but allow infrared radiation to pass through. In visible light surveys, these regions can appear dim or absent, even when star formation rates are high. Webb's infrared instruments are sensitive to this emission, allowing entire populations of galaxies to emerge where earlier surveys recorded little or nothing. At the same time, advances in image processing matter. Webb's deep fields are built from thousands of individual exposures combined through carefully calibrated pipelines. This stacking increases sensitivity and allows astronomers to distinguish real sources from noise with far greater confidence than was possible in earlier eras. The result is not just more light, but more reliable detection of extremely faint objects. A catalog containing hundreds of thousands of objects, however, does not mean that each entry is equally well understood. Detection and classification are not the same thing. Detection establishes that a source exists above a defined confidence threshold. Classification attempts to determine what kind of object that source is. Photometry measures brightness across different wavelengths, providing color information and rough physical properties. Morphology describes shape and structure, which becomes more uncertain as objects grow fainter and smaller in apparent size. Redshift estimation can be inferred statistically from photometric data, but spectroscopic confirmation requires much more observing time and is available for only a fraction of sources. Large catalogs, therefore, contain layers of certainty, with some objects characterized in detail and others represented primarily as statistically significant detections. This shift in scale changes how astronomy operates. Instead of focusing primarily on a small number of exceptionally detailed objects, research increasingly relies on population statistics. Distributions, trends, and correlations across tens or hundreds of thousands of galaxies become more informative than any single example. Questions move away from whether a particular galaxy is unusual and toward how common certain properties are across cosmic time. This does not eliminate the value of detailed follow-up observations, but it does change where confidence comes from. Patterns seen consistently across large samples carry a different weight than isolated discoveries. The increase in galaxy counts also has broader implications. If the total number of galaxies in the observable universe is higher than previously estimated, then the inferred number of stars and planets scales accordingly. If each galaxy hosts billions of stars, and if many of those stars host planetary systems, then increasing the galaxy count by an order of magnitude increases those totals by the same factor. This scaling is mathematically straightforward, but it rests on assumptions that require careful testing. Deep fields sample small regions of sky, and those regions may not be perfectly representative of the universe as a whole. Cosmic variance means that some areas are denser than others. For this reason, astronomers are cautious. Wider area surveys at slightly lower depth are underway to determine whether the high densities seen in deep fields persist across different directions and environments. An illustrative scenario helps clarify how this scaling works. Imagine that a previous estimate placed the total number of galaxies at 200 billion, based on visible light surveys. If new infrared observations suggest that the true number might be 10 times higher, then estimates of total stellar populations and potential planetary systems also increase by roughly the same factor. The scaling itself is valid. What remains under refinement is the initial input value. As more surveys expand coverage and improve completeness, that number will be adjusted, constrained, and potentially revised again. What Webb's deep fields have done is not to provide a final count, but to demonstrate that earlier counts were incomplete in a systematic way. By revealing large populations of faint, red-shifted and dust-obscured galaxies, Webb has shifted the baseline expectation. The universe appears more crowded than it did before, not because galaxies suddenly formed, but because instruments finally became capable of detecting them. And once that baseline shifts, every inference built on it must be revisited with the same level of care. The phrase, "too much light too early," sounds dramatic, but what it actually compresses is a specific observational tension. When astronomers measure the total amount of light coming from galaxies in the first few 100 million years after the Big Bang, they find values that are higher than what many models predicted. This does not mean the early universe was glowing in some undefined way. It means that when brightness is translated into physical quantities, the numbers do not line up cleanly with expectations. Light in this context is a proxy. It reflects how many stars exist, how massive those stars are, how efficiently gas was converted into stars, and whether additional sources of radiation contributed to the total signal. There are several ways early galaxies could appear more luminous than predicted. One possibility is simply that there were more stars than models allowed for at that time. Another is that stars were, on average, brighter, which could happen if the distribution of stellar masses was different, favoring more massive stars that burn hotter and emit more radiation. A third contribution could come from non-stellar sources, such as actively feeding black holes at galactic centers, which can produce enormous amounts of light relative to their size. There is also the possibility that some portion of the discrepancy arises from measurement effects, including selection biases or uncertainties in how dust absorption and emission are modeled. Each of these options changes the interpretation in a different way, and none can be evaluated in isolation. Several mechanisms could plausibly raise luminosity in the early universe without invoking unknown physics. Star formation efficiency is one of them. If early galaxies converted a larger fraction of their available gas into stars over shorter timescales, their brightness would increase accordingly. Conditions in the early universe were different. Matter was denser, galaxies were closer together, and mergers occurred more frequently. Gas inflow along large-scale filaments could deliver fresh material continuously, sustaining high star formation rates. These factors can increase the rate at which stars form without requiring new physical laws. Another lever is the initial mass function, which describes how many stars form at different masses. If early star formation favored more massive stars than seen today, total luminosity would rise, even if the total stellar mass did not change dramatically. When observations strain models in this way, Cosmology does not respond by discarding its framework outright. Models are built from many interconnected assumptions and parameters, and tension indicates that some of those inputs may need adjustment. This process is referred to as model strain. Simulations and semi-analytic models are updated iteratively. Feedback processes are refined to better capture how energy from stars and black holes affects surrounding gas. Dust models are improved to account for how light is absorbed and re-emitted. Contributions from active galactic nuclei are reassessed to determine how much of the observed light originates from accretion rather than stars. Each update is tested against the full range of observations, not just a single anomaly. This iterative process is not a sign of weakness. It is how complex models evolve. A model that survives multiple rounds of strain and refinement becomes more reliable, not less. What matters is whether adjustments remain consistent with other observations, such as the cosmic microwave background, large-scale structure, and chemical abundances. In that sense, tension becomes a productive force. It directs attention to where understanding is incomplete. An illustrative example helps clarify why this issue matters. Imagine a model predicts a certain luminosity density for galaxies at a given early epoch. Observations then indicate a value 2 to 10 times higher. This range is not a small discrepancy that can be absorbed by minor calibration changes. A factor of 2 already requires meaningful changes in assumptions. A factor of 10 demands a reevaluation of multiple processes simultaneously. This is why too much light too early is taken seriously. It signals that early galaxy formation may have proceeded more efficiently or differently than previously assumed. What Webb has provided is not a final answer, but a clearer view of the mismatch. By extending observations deeper into the infrared and capturing faint, distant galaxies in large numbers, it has made the discrepancy harder to ignore and easier to quantify. The question now is not whether early galaxies were brighter than expected. It is which combination of mechanisms best explains why. One of the most persistent tensions highlighted by Webb's observations is not simply that galaxies appear early, but that some of them appear unexpectedly mature. These galaxies are large for their age, bright in a way that suggests substantial stellar populations, and chemically evolved beyond what many models anticipated. Chemical maturity is especially important because it functions as a kind of clock. In the early universe, the material available after the Big Bang consisted almost entirely of hydrogen and helium. Elements heavier than these are produced inside stars. They appear only after stars have formed, lived out their lifetimes, and released processed material back into their surroundings through winds or explosive events. Detecting these heavier elements therefore implies that multiple generations of stellar activity must have already occurred. This is why chemical composition carries such weight in these discussions. When astronomers observe signatures of elements like carbon, oxygen, or nitrogen in very early galaxies, they are not just identifying what the galaxy contains. They are inferring a sequence of events. Stars must have formed from primordial gas. Some of those stars must have been massive enough to evolve quickly. They must have ended their lives in ways that returned enriched material to interstellar space. New stars must then have formed from that enriched gas. Each step takes time, and together they define a minimum timeline that cannot be compressed arbitrarily. These claims rest on spectroscopy, not on visual appearance alone. When Webb observes a distant galaxy, its instruments can separate incoming light into its component wavelengths. Specific elements absorb and emit light at well-defined wavelengths, creating patterns known as spectral lines. By measuring the presence and relative strength of these lines, astronomers infer which elements are present and in what proportions. This information is then combined with models of stellar evolution and nucleosynthesis to estimate how long those elements would take to accumulate under different conditions. The inference chain runs from detected photons to calibrated spectra to elemental abundances, and finally to constraints on evolutionary history. The challenge emerges when this inferred history seems to require more time than the universe had available at that epoch. This is sometimes described as a timeline compression problem. It is not simply that galaxies exist early. It is that several processes that normally unfold over extended periods appear to have already taken place. Stars must have formed efficiently. Some must have been massive, with short lifetimes. Enrichment must have proceeded rapidly, and the resulting stellar populations must have assembled into structures large enough to be detected at great distances. Each of these steps has a minimum duration governed by physics, even though the exact timescales depend on assumptions about star formation efficiency and mass distribution. Stellar lifetimes are a key factor here. Massive stars evolve quickly, sometimes in only a few million years, while smaller stars live much longer. A population dominated by massive stars can enrich its surroundings rapidly, but such populations also affect luminosity and feedback processes. The speed of chemical enrichment, therefore, depends strongly on the mix of stellar masses. Adjusting that mix can ease some tensions while creating others. This interconnectedness is what makes the problem challenging rather than contradictory. An important point emphasized in the source is that these observations do not hinge on a single unusual object. Early claims often focused on individual galaxies that seemed extreme, raising the possibility that they were rare outliers or misidentified. What Webb has shown across multiple deep fields and independent surveys is that similar properties appear repeatedly. When trends persist across populations, they carry more weight than isolated cases. Populations reveal whether models systematically underpredict certain outcomes, whereas single objects can often be explained away. This distinction matters for how models are tested. A lone anomaly can be accommodated without major revisions. A consistent population-level discrepancy demands attention. Webb's observations suggest that early galaxies with substantial size, brightness, and chemical enrichment are not isolated curiosities. They represent a class of objects that appears more common than previously expected. That does not mean existing models are invalid, but it does mean they must account for these populations in a way that remains consistent with everything else we observe. The result is not a collapse of cosmology, but a tightening of constraints. The early universe appears to have been capable of building complexity faster than earlier visible light data implied. Understanding how that happened requires tracing multiple processes simultaneously, from star formation to feedback to chemical enrichment. And it requires treating these galaxies not as exceptions, but as part of a broader statistical picture that any successful model must explain. Black holes sit at the center of this story because they concentrate several independent constraints into a single problem. Webb's observations indicate that very massive black holes were already present when the universe was only a few 100 million years old. This immediately raises questions, because black hole growth is not unconstrained. In standard scenarios, black holes grow by accreting surrounding matter. That process releases energy, and that energy pushes back on the inflowing material. The result is a natural limit on how fast mass can accumulate. Even under optimistic assumptions, growing from a stellar mass seed to a supermassive black hole takes time. When observations place extremely massive black holes at very early epochs, they push against those growth limits. The difficulty is not that black holes exist early, but that their inferred masses appear too large given the available time. If a black hole starts as the remnant of a massive star, its initial mass is modest on cosmic scales. To reach millions or billions of solar masses, it must accrete continuously at or near the maximum allowed rate for extended periods. Interruptions slow growth. Inefficiencies matter. The early universe offers less time for these processes to unfold, which is why the presence of very massive black holes so soon after the Big Bang stands out. Several candidate explanations are discussed in the source, and each addresses a different part of the constraint. One possibility is direct collapse. In this scenario, under specific conditions, large clouds of gas collapse directly into a massive black hole without first forming stars. This bypasses the slow buildup from small seeds and provides a head start. Another possibility is merger-driven growth. In a denser, early universe, black hole mergers could have been more frequent, allowing mass to accumulate faster than through accretion alone. The source also mentions the idea of dark stars, hypothetical objects powered by interactions involving dark matter that could grow to enormous sizes before collapsing into black holes. This idea remains speculative. In scientific terms, speculative does not mean arbitrary. It means mathematically plausible within known physics, but lacking direct empirical support. A speculative idea may satisfy equations and avoid contradictions, yet still await observational confirmation. dark stars fall into this category. They are consistent with certain models, but have not been directly observed. As such, they are considered possible contributors rather than established solutions. Black holes matter not only because of their own growth, but because of how they interact with their host galaxies. As matter falls toward a black hole, energy is released into the surrounding environment. This energy can heat nearby gas, drive powerful outflows, and change the conditions under which stars form. In some cases, this can trigger bursts of star formation by compressing gas. In others, it can suppress star formation by heating gas and preventing it from collapsing. This feedback links black hole growth directly to galaxy evolution. This connection becomes important when interpreting early galaxy brightness. If a galaxy hosts an actively accreting black hole, a significant fraction of its light may come from that process rather than from stars. If that contribution is not fully accounted for, the galaxy's stellar mass can be overestimated. The source describes how reanalysis of some early galaxies reduced their inferred masses once black hole contributions were included. Objects initially labeled as extreme outliers became less problematic when this adjustment was made. This is a clear example of partial repair. The discrepancy does not vanish entirely, but it shrinks. The most extreme cases become more compatible with models, while a residual tension remains. This pattern is common in cosmology. New data reveal a problem. Reanalysis explains part of it. What remains guides further investigation. Early black holes, therefore, illustrate how Webb's observations both challenge and refine existing frameworks. They force closer attention to growth limits, feedback processes, and the assumptions built into mass estimates. They also show how apparent contradictions can soften as models incorporate more realistic physics. The problem is not solved, but it is better defined. And in science, defining the problem precisely is often the most important step toward resolving it. The claim about population 3, or so-called monster stars, rests on chemical evidence rather than direct observation. The source points to unusual ratios of nitrogen to oxygen detected in the spectra of very distant galaxies. These ratios stand out because they differ from what is typically produced by later generations of stars. In astrophysics, abundance ratios are powerful diagnostic tools. Different nuclear processes inside stars produce elements in characteristic proportions. When those proportions appear in interstellar gas, they carry information about the types of stars that must have existed earlier. Nitrogen and oxygen are created through different pathways during stellar evolution. Oxygen is produced efficiently in massive stars and released when they end their lives, while nitrogen production can be enhanced under specific conditions associated with very massive stellar cores. When astronomers detect nitrogen to oxygen ratios that are difficult to reproduce with standard stellar populations, they consider whether alternative stellar histories could explain the pattern. In this case, The source argues that extremely massive early stars could naturally generate such ratios during their brief lifetimes. It is important to be clear about what kind of evidence this represents. Webb is not imaging individual first-generation stars. Those objects would be far too small and distant to resolve directly. Instead, the evidence is indirect. It comes from the chemical imprint left behind in later gas and stars. This imprint acts as a downstream record of earlier processes. Inference based on chemical signatures requires caution. Multiple scenarios can sometimes produce similar patterns, and distinguishing among them depends on how well models reproduce the full set of observed ratios across different elements. In science, matching a predicted signature increases confidence, but it does not establish absolute proof. Alternative explanations must be evaluated and ruled out as far as possible. This is why such findings are described in probabilistic terms rather than as definitive detections. The strength of the claim depends on how uniquely the observed ratios point to one class of progenitors over others. The reason this matters extends beyond stellar archaeology. If extremely massive stars existed early, they would have had short lifetimes and large final masses. When such stars collapse, they can form black holes that are much more massive than those produced by ordinary stellar deaths. These larger initial seeds reduce the time required for subsequent growth through accretion or mergers. In this way, early massive stars provide a potential link between chemical signatures and the black hole growth problem. The logic is straightforward. If black holes start larger, they need less time to reach the masses observed at early epochs. This does not eliminate the need for efficient growth, but it eases the most severe constraints. Population 3. Stars, if they existed in the extreme form suggested, could therefore play a role in reconciling early black hole observations with physical limits on accretion. What Webb contributes here is not a final answer, but a set of measurements that allow these possibilities to be evaluated more seriously than before. By detecting detailed chemical patterns at high redshift, it opens a window into processes that cannot be observed directly. The challenge now is to determine how unique those patterns really are, and how consistently they appear across different early environments. One of the most consistent claims in the source is that galaxies are not distributed randomly through space. Instead, they trace out a connected network of filaments and dense nodes known as the cosmic web. This pattern matters because distribution is one of cosmology's most sensitive tests. Large-scale structure emerges from the interaction between gravity, matter content, and the universe's expansion history. When simulations and observations agree on how matter is arranged across enormous distances, it indicates that the underlying physics is being captured correctly. The cosmic web is not inferred from a single type of observation. It appears when galaxy positions are mapped in 3 dimensions, revealing concentrations and voids rather than uniform spacing. These patterns are predicted by models in which matter initially had small density variations that grew over time under gravity. The details of the resulting structure depend on how much matter exists, how it behaves, and how it interacts gravitationally. Because of this, the web serves as a powerful constraint. A model that fails to reproduce large-scale distribution is difficult to reconcile with reality, regardless of how well it explains individual objects. In the framework presented in the source, dark matter plays a central role in shaping this structure. Dark matter is inferred to make up the majority of the universe's matter content, and it interacts primarily through gravity. Evidence for its existence comes from several independent categories of observation. Galaxy rotation curves show that visible matter alone cannot account for observed motions. The dynamics of galaxy clusters indicate far more mass than can be seen directly. Gravitational lensing reveals mass distributions that extend beyond luminous components. Each line of evidence points to the same conclusion. There is more gravitating matter present than what emits light. It is important to separate what is observed from what is inferred. Astronomers do not observe dark matter particles directly. They observe gravitational effects that require additional mass to explain them. The inference is robust because it appears across different scales and measurement techniques, but it remains an inference grounded in consistent observational patterns rather than direct detection. The source highlights filament detection through gravitational lensing as a particularly significant example. Gravitational lensing occurs when mass bends the path of light traveling from distant galaxies. This bending produces small distortions in the shapes of background galaxies. By measuring these distortions across large areas of sky and combining many weak signals, statistically, astronomers can reconstruct the distribution of intervening mass. Detecting filaments this way is challenging because the distortions are subtle and easily masked by noise, instrumental effects, or intrinsic galaxy shapes. Accurate detection requires careful calibration, stacking of many observations, and rigorous error correction. Confirming filaments through lensing matters because it tests the cosmic web model at smaller and more detailed scales. Large-scale clustering has been established for decades, but observing the fine-grained structure of filaments provides an additional layer of validation. When the predicted mass distribution appears where models expected, confidence in that part of the framework increases. This is where an important contrast emerges. In some areas, such as large-scale structure, and the existence of a cosmic web shaped by dark matter, observations align closely with predictions. In other areas, such as early galaxy brightness and black hole growth, tensions remain. Seeing both outcomes side by side is informative. It shows that the framework is not uniformly failing or uniformly succeeding. It is strong where predictions have been tested extensively, and under strain where new observational regimes push beyond earlier limits. This contrast keeps the narrative grounded. Webb's observations are not overturning everything at once. They are refining some components while stressing others. The cosmic web stands as an example of a structure that continues to match expectations, even as other aspects of early cosmic history prompt revision. Voids represent the opposite extreme of the cosmic web. They are regions where matter density is far below average, containing relatively few galaxies and very little mass compared to filaments and clusters. In the source, voids are emphasized not as empty curiosities, but as valuable environments for measurement. Their importance comes from what they lack. With fewer massive structures nearby, local gravitational effects are reduced. Galaxies inside voids are less influenced by the complex motions caused by nearby clusters and dense filaments. This makes their behavior easier to interpret in terms of large-scale expansion rather than local dynamics. Because of this simplicity, voids act as clearer probes of cosmic expansion. When astronomers measure how galaxies move relative to one another inside dense regions, the signal is mixed. Expansion, gravitational attraction, and past interactions all contribute. In voids, the dominant influence is the overall expansion of the universe itself. This cleaner signal allows tighter constraints on how fast space is expanding and how that rate changes over time. In that sense, voids are not gaps in the data. They are controlled environments where certain effects are minimized. This clarity becomes especially relevant when discussing dark energy. In the source's narrative, dark energy accounts for roughly 68% of the universe's total energy density. Its defining feature is that its density remains approximately constant as the universe expands. This statement can sound abstract, but its implication is straightforward. As space grows larger, the total amount of dark energy increases because the density stays the same while the volume increases. Unlike matter or radiation, which become more dilute as space expands, dark energy does not thin out in the same way. Within this framework, dark energy gradually comes to dominate the universe's dynamics. Early in cosmic history, matter played the leading role in shaping structure. Over time, as expansion continued and matter spread out, dark energy's influence grew. Eventually, it became the primary driver of accelerated expansion. This acceleration is not inferred from a single observation, but from multiple lines of evidence, including distant supernova measurements, large-scale structure, and the cosmic microwave background. The consequences of accelerated expansion become more pronounced with time. As expansion speeds up, horizons matter more. There is a limit to how far light emitted today can ever travel toward us. Galaxies that are currently visible will eventually cross that limit. Their light will stretch to wavelengths that are no longer detectable and then stop arriving altogether. According to the source, this means that in the far future, fewer galaxies will remain observable. The sky will contain less information about the broader universe than it does now. This has direct implications for the future of cosmology. Measurements that rely on observing distant galaxies, tracing large-scale structure, or comparing conditions across cosmic time will become more difficult or impossible. Future observers will have access to a smaller observable universe, even though the total universe continues to expand. In this sense, the present era is unusually informative. Many of the signals needed to reconstruct cosmic history are still accessible. Voids, therefore, play a dual role. They help clarify how expansion behaves now, and they illustrate what will be lost as expansion accelerates. By studying regions where gravitational complexity is minimized, astronomers can better isolate the influence of dark energy. And by understanding how horizons evolve, they can anticipate which kinds of measurements will remain possible and which will fade with time. The Hubble tension is often described in dramatic terms, but in practice, it functions as a diagnostic rather than a scandal. As presented in the source, the tension refers to a persistent difference between two ways of measuring the universe's expansion rate. Methods that infer the rate from conditions in the early universe yield a value near 67 kilometers per second per megaparsec. Methods that measure distances and motions in the nearby universe produce a higher value, closer to 73. Both results are derived from careful observations, and both have been repeatedly tested. Disagreement between methods does not automatically imply error. The two approaches rely on different data, different assumptions, and different links in the inference chain. Early universe methods interpret patterns in the cosmic microwave background to infer how fast the universe should be expanding today. This requires assuming a specific cosmological model and extrapolating forward in time. Late universe methods build a distance ladder, calibrating nearby objects and extending outward through successive steps. Each approach has its own sources of uncertainty and its own sensitivity to systematic effects. Because they probe different epochs, a mismatch can arise either from measurement issues or from incomplete modeling. Webb's role in this story is focused and important. According to the source, Webb's observations support the late universe distance ladder by providing independent measurements that align with previous results. This matters because it reduces the likelihood that the discrepancy arises from a simple calibration error in earlier telescopes. When an independent instrument with different design choices and sensitivities reproduces the same outcome, confidence in that measurement increases. This does not resolve the tension, but it changes how it is interpreted. If late universe measurements are reinforced, attention shifts toward other possibilities. Either the early universe inference is missing something subtle, or the standard model needs adjustment to accommodate new physics. Alternatively, smaller systematic effects could still be present in one or both methods, but they would need to be both subtle and coherent to produce the observed gap. An illustrative uncertainty breakdown helps clarify why this issue is challenging. Imagine that each step in a measurement chain carries a small calibration uncertainty, perhaps only a few percent. Individually, these uncertainties might seem negligible. When combined across multiple steps, however, they can accumulate. A slight bias in distance calibration, compounded over many rungs of the ladder, can shift the final value noticeably. At the same time, early universe methods are sensitive to assumptions about particle content, energy densities, and initial conditions. Small changes in those assumptions can propagate forward to affect the inferred expansion rate. The key point is that the discrepancy is statistically significant. It exceeds the level expected from random fluctuations alone. That is why it persists as an open problem. But statistical significance does not dictate the explanation. It signals that something deserves closer scrutiny. Whether that something turns out to be a hidden systematic, a refinement of existing models, or genuinely new physics remains uncertain. Seen this way, the Hubble tension is not a failure of cosmology. It is a focused probe of where understanding is incomplete. Webb's contribution is to sharpen that probe by strengthening one side of the comparison. As the range of plausible explanations narrows, the tension becomes more informative, guiding future observations and theoretical work, rather than undermining the framework as a whole. The concept of a cosmic horizon introduces a hard boundary that is often misunderstood as a technological limitation rather than a physical one. In the source, the horizon is defined as a causal boundary. Regions beyond it cannot send signals that will ever reach us. This is not a statement about the power of telescopes or the sensitivity of detectors. It is a statement about space-time itself. Light, gravitational waves, or any other carrier of information emitted beyond that boundary will never arrive, no matter how long we wait. Expansion increases the separation faster than signals can close the gap. In operational terms, this means that information from those regions is permanently inaccessible. The limitation is built into the structure of the universe, not into our tools. This boundary changes how observation is framed. Everything we know about the universe comes from within our observable region, defined by how far signals have been able to travel since the beginning of cosmic expansion. Beyond that region, conditions may be similar or different, but they are not testable by direct observation. This leads to the idea that every location in the universe has its own observable universe. An observer in a distant galaxy would see a different set of galaxies within their horizon, even though the physical laws governing both regions are assumed to be the same. This matters because cosmology relies on the assumption that what we observe is typical. This assumption is known as the cosmological principle. It states that, on large enough scales, the universe is homogeneous and isotropic, meaning it looks roughly the same everywhere and in every direction when averaged over sufficient volume. The source treats this as an assumption rather than a proven fact. It is adopted because observations within our horizon support it, and because it allows models to be tested and predictions to be made. Without it, cosmology would lose much of its explanatory power. Falsifying the cosmological principle would require observing systematic differences across large regions of the sky that cannot be explained by local effects or statistical variation. So far, no such evidence has been found. The cosmic microwave background, large-scale structure surveys, and galaxy distributions all appear consistent with large-scale uniformity. But it is important to remember that this conclusion applies only to the observable universe. It cannot be directly extended beyond the horizon. The source includes a communication thought experiment to clarify what these limits imply. In principle, communication with extremely distant regions may be possible if those regions lie within the horizon. A signal could be sent, and given enough time, a response could arrive. But the timescales involved can be so long that communication becomes functionally irrelevant. Exchanges would span tens of billions of years, far exceeding the lifespan of civilizations, planets, or even stars. In such cases, the distinction between possible and practical becomes significant. At greater distances, communication is not merely impractical, it is impossible. Signals emitted beyond the horizon will never reach us, and signals we send will never reach them. This creates isolated regions that are causally disconnected, even though they are part of the same universe. Each region evolves according to the same physical laws, but without any exchange of information. Understanding this limit reshapes how cosmology is interpreted. It highlights that our picture of the universe is necessarily partial, constrained by causal structure rather than observational ambition. It also underscores why models must be judged by how well they explain what lies within reach, not by speculation about what lies beyond. The horizon is not a philosophical boundary. It is a physical one, and it defines the ultimate scope of what science can directly test. What Webb ultimately changes is not just the list of objects we can observe, but how science itself advances when a new window opens. Instruments are not neutral recorders of reality. They define which signals matter, which questions are practical, and which assumptions remain unchallenged. By extending access deep into the infrared, Webb revealed populations of galaxies, stars, and energetic processes that were largely invisible before. That does not mean those populations suddenly appeared. It means earlier, theories were built around an incomplete sample. When new data arrive, the task is not to discard what worked, but to reassess which assumptions were shaped by limited visibility. This is why discovering more often means relearning. Models are constructed to explain the data available at the time. When the data space expands, those models are tested in new regimes. Some predictions remain accurate, others require adjustment. This is not a sign of failure. It is the expected behavior of a scientific framework responding to better evidence. Webb's impact lies precisely here. It pushes cosmology into regions where extrapolation becomes observation, forcing parameters to be recalibrated rather than principles to be abandoned. Public communication often struggles with this distinction. When results are summarized outside the scientific context, they are frequently framed as reversals. Phrases like, "everything we thought was wrong," capture attention, but they flatten nuance. Scientists do not usually mean that foundational ideas have collapsed. They mean that the parameter space has shifted. Estimates move. Ranges narrow or widen. Processes once thought rare turn out to be common, or vice versa. The underlying structure of the theory often remains intact. In this case, several elements are robust. The expansion of the universe is well established. redshift as a measure of cosmic history remains sound. The existence of large-scale structure and the role of gravity in shaping it are supported by multiple independent observations. These pillars are not in question. What is in motion are the details. How efficiently stars formed in the early universe. How massive the first black hole seeds were. How many faint, dust-obscured galaxies populate deep cosmic time. How representative early surveys were of the universe as a whole. Headlines compress uncertainty because uncertainty is difficult to convey. A range of plausible explanations becomes a single dramatic claim. But inside the scientific process, uncertainty is not a weakness. It is a map of where attention is focused. Webb sharpens that map. It tells researchers which questions are settled enough to rely on, and which ones are still open enough to explore. In that sense, Webb's most important contribution may be procedural. It demonstrates how scientific knowledge changes in response to new instruments, not by erasing what came before, but by revealing where confidence was justified and where it was provisional. It shows that progress often looks less like overturning and more like refinement. And it reminds us that every clear picture of the universe is to some extent shaped by the tools used to see it. The scale revealed by modern cosmology imposes constraints that are not abstract but practical. Distances measured in billions of light years define hard limits on travel, communication, and coordination. Even at the speed of light, which remains an upper bound, crossing the observable universe would require timescales far exceeding the lifespan of stars, planets, or biological civilizations. These constraints shape how exploration is conceived. They place clear boundaries on what can be visited, what can be communicated with, and what can only be inferred remotely. In this context, ambition becomes a matter of prioritization rather than reach. Efforts focus on understanding nearby environments in detail, while using observation and inference to study the farthest ones. The scale of the universe does not diminish inquiry, but it forces it to operate within strict physical limits. These limits also affect how detection is framed. Signals weaken with distance. Information arrives delayed. The farther a phenomenon lies, the less complete the data become. This reality influences long-term strategies in astronomy and planetary science. It emphasizes the importance of extracting maximum information from the signals that do arrive, and of building instruments capable of detecting faint, distant sources with precision. It also reinforces the value of indirect methods, statistical approaches, and population-level analysis. Scale does not simply make goals harder. It reshapes which goals are meaningful. The source also highlights a quieter but significant shift in how data are shared. Webb's observations are released publicly, along with catalogs, measurements, and tools that allow researchers worldwide to analyze them. This democratization changes who can participate in discovery. Access to data is no longer limited to a small number of institutions with exclusive observing time. Researchers with different perspectives, methods, and questions can work from the same foundation. This openness accelerates innovation by increasing the number of independent analyses and by exposing assumptions to broader scrutiny. The implications extend beyond efficiency. Open data reduce structural inequality in scientific participation. Institutions without large observatories or extensive funding can still contribute meaningfully. Ideas compete on analytical strength rather than on access alone. At the same time, openness increases the pace of revision. Claims are tested more quickly. Errors are identified sooner. Confidence builds through replication rather than authority. In this sense, scale influences not only what is studied, but how knowledge is produced. The source closes by returning to a familiar conclusion in the history of astronomy. Humanity does not occupy a central or privileged position in the universe. This is not presented as a philosophical statement, but as a recurring outcome of measurement. Each expansion of observational capability has reduced perceived centrality. Earth was displaced from the center of the solar system. The Sun was shown to be one star among many. The Milky Way became one galaxy among countless others. Now, even the Milky Way appears as a typical member of a vast population, distributed across a structure far larger than once imagined. This pattern persists because perception follows scale. As measurements improve, reference points shift outward. What once seemed unique becomes typical when placed in a larger context. This does not diminish the significance of human activity. It reframes it. Significance becomes local rather than cosmic, defined by conditions, constraints, and relationships rather than by position. Seen this way, the societal meaning of scale is not about insignificance or awe. It is about clarity. The universe is large. Information is limited by physics. Knowledge advances through instruments, inference, and revision. Webb's contribution is to sharpen that clarity. It does not offer comfort or spectacle. It provides boundaries within which understanding can grow. What emerges from Webb's observations is not a single headline result or a single revised number. It is a set of pressures applied across the entire structure of modern cosmology, each one testing a different assumption that had become comfortable over time. Distance, which feels intuitive at human scales, turns out to be deeply model-dependent when expansion is taken seriously. The difference between how far light has traveled and where its source is now is not a technical detail. It is foundational. Without that distinction, the size of the observable universe makes no sense. With it, the apparent contradiction dissolves, but only by forcing us to abandon everyday intuition. The same pattern appears in the revised Galaxy Census. When observation expands into new wavelength regimes, especially the infrared, the universe becomes more crowded. Populations that were faint, dust-obscured, or heavily redshifted move from the margins of detection into the core of statistical analysis. This naturally increases estimates of how many galaxies exist, and by extension, how many stars and planets they contain. But Webb has not delivered a final count. It has exposed how incomplete earlier surveys were, and why representativeness must be tested rather than assumed. Deep fields offer unprecedented depth, but they sample small regions. Ongoing and future surveys are required to determine how typical those regions really are. Early universe brightness and structure create a more specific kind of tension. The issue is not that galaxies appear early, but that they appear bright, massive, and chemically evolved in ways that compress multiple timelines at once. Star formation, chemical enrichment, and structural assembly all seem to proceed faster than many models predicted. This does not invalidate the broader framework of structure formation, but it does challenge assumptions about efficiency, feedback, and initial conditions. The phrase, "too much light too early," captures attention, but its real significance lies in what it forces modelers to reconsider. In several cases, apparent anomalies diminish when additional factors are included. Accounting for black hole contributions reduces inferred stellar masses in some early galaxies. Improved dust modeling alters luminosity estimates. Better understanding of feedback changes how energy flows through forming systems. These adjustments do not erase tension entirely, but they demonstrate how science self-corrects. New data reveal a mismatch. Reanalysis explains part of it. What remains becomes a sharper, more focused problem rather than a vague contradiction. This iterative narrowing is not a sign of instability. It is the mechanism by which complex theories become more precise. The documentary has also shown where confidence remains strong. Large-scale structure, the existence of a cosmic web, and the role of gravity in shaping it continue to align with predictions. Dark matter, while not directly observed, is supported by multiple independent lines of evidence that converge on the same conclusion. Voids provide clean environments for studying expansion. Lensing confirms mass distributions where models expect them. In these areas, Webb reinforces rather than disrupts existing understanding. The contrast between strength and strain is itself informative. It shows that cosmology is not uniformly uncertain. It is selectively challenged where new observational regimes have opened. Underlying all of this is a hard boundary that no instrument can cross. Horizons impose limits on information that are built into space-time itself. Beyond a certain distance, signals cannot arrive, regardless of technological progress. Every conclusion drawn in cosmology is therefore conditioned on what can reach us. Each observer, in each location, has access to a different observable universe. The assumption that our observable region is typical is well supported by available evidence, but it remains an assumption constrained by causal limits rather than direct verification. Taken together, Webb's impact is best understood not as a revelation, but as a clarification. It clarifies which aspects of our models are anchored by multiple lines of evidence and which depend sensitively on observational reach. It clarifies how much of our confidence was earned and how much was provisional. It clarifies the difference between what is measured directly and what is inferred through layers of modeling and calibration. This leads naturally to a deeper question, one that does not arise from speculation but from the logic of the evidence itself. If our best theories are constructed entirely from information that can reach us, and if the universe contains regions that never will, how do we distinguish a universal law from a pattern that appears universal only because we have not yet seen beyond its domain?